Hello, Math 1030. This is lesson 11B. There is no 11A, so you don't have to worry about that one. Today's lesson is about symmetry and tilings. I don't think it's super difficult, but be warned on the homework, there is only 5 questions, but there are a couple of questions that have like multiple parts. So I don't think it's going to be time consuming, but there's at least one that has like 5 parts. Okay, so symmetry and tiling. You already know a lot about symmetry, but just as a quick review, symmetry refers to kind of balance or repetition that a shape has. So reflection symmetry is when the object remains unchanged when it's reflected across a straight line. So we have a letter A right here that has some left-right reflection symmetry. If it's reflected over a vertical line, it is the same. And the letter H right here has both left, right, and top bottom reflection symmetry. So we could reflect it about this vertical line and it would be the same appearance. And we could also reflect it horizontally and it would have the same appearance. So those are reflection symmetries. Rotational symmetries are if the object remains unchanged when it's rotated through some angle about a point, and the angle does matter for different shapes. That rotational symmetry angle will be different. So if we rotate the letter O or the letter S, for example, those would be having some rotational symmetry. Both of those have rotational symmetry of a rotating angle of 180 degrees. So just to kind of remind you what that rotational angle means, if I rotated it, say 90 degrees, this would not be the same. If I rotate it 180, that's where it has the same shape. And the font that I have is like not perfect. It's not exactly perfect, but you get the idea. So rotating it like 30 degrees wouldn't do it. Rotating it 270 wouldn't do it. And then 360 would be considered, like that you're just back where you started. So this would be, if I wanted it to say what its rotational angle would be, it would be 180. Okay, so symmetries in stars and regular polygons is what your homework is going to focus on, not letters. So in general, if we are dealing with stars, regular stars, they have a certain number of reflection symmetries and a certain number of rotational symmetries. So if you have a star or a shape that has n points, then it is going to have that same number of reflection symmetries, and it will have one less rotational symmetry. So it has n reflection symmetries and n minus 1 rotational symmetries, depending on how many points it has. And we'll do a couple examples so you'll get what that means. And then you can find the degrees of rotation for rotational symmetry by dividing 360 degrees by n, and then you'll count out by that increment and you'll have n minus 1 answers. So that's a lot of words, but you'll get it. We're going to do this square shape first, and then we'll do a star. So this square would have, it would have n reflection symmetries. Now this is a four-sided shape or four-pointed shape. So it's going to have, so that's our n. So it's going to have n equals 4 reflection symmetries. Now, with a square, it's actually kind of interesting. The reflection symmetries for a square are here, here. Oh, that's bad. I can draw, at least move it up a little bit. And then also the other two reflection symmetries for a square are here and here, the diagonals. So it does have 4 reflection symmetries. You don't have to draw the reflection symmetries on your homework or anything. You'll just have to type in the 4. And then for the rotational symmetries, that's a little bit trickier. There are only 3 of them. So 4 minus 1 is 3. We have 3 rotational symmetries. So the rotational symmetries, to calculate those, you take 360 and you divide it by n. So we're going to divide by 4. Now, be careful here. You don't divide by 3. You do divide by n. It's not n minus 1 that you're dividing by. So you divide by n. In this case, 360 divided by 4 is 90. And this is like what we're going to count by to get our answers. So our first answer would be a 90-degree rotation. And so I will just show you what that 90-degree rotation would look like. So if we rotated this 90 degrees, boom, it's the same. And then we're going to count by 90. So we're going to do what we're starting with 90 now. And we're going to add another 90 to get 180. That's our next answer. So 180 degrees of rotation, if my square started like this, 180 would be this green dot at the bottom now, 180-degree rotation. So that's the same. And then I need to have n minus 1 answers. So I should have 3 answers here. So there is one more answer. And so I'll take that 180 degrees and I'll add another 90 because I'm counting by 90. That takes me to 270. And that's my final answer. The 270 would be rotating so that the top's edge is 90, 180, 270 over here on the side. Now, a quick check here that you can do is that if I add my count by one more time, if I add 90 to 270, I'll get back to 360. So if you add that last one, you're back to where you started. And we don't count that one. So that's why you have one less answer than the number of reflection symmetries, because that last one, that fourth one would just be if it, rotated 360 degrees, so we don't count it. So our 3 answers for our angles of our rotational symmetry are 90, 180, and 270. So let's try that again with a star. That's a 5-pointed star. So the number of points is 5, so it has 5 reflection symmetries. I'm going to draw those just for fun. There's 1, 2, 3, 4, and 5. So those are the 5 reflection symmetries. Now for the rotational symmetries, we know that there will be one less rotational symmetry. So there are only 4, and that comes from subtracting 1. So if we wanted to put in our answer for how many degrees the star could be rotated so that it remains unchanged, we are going to have 4 answers here to go with our 4 rotational symmetries. To find those 4 answers, we're going to take 360 and divide it by 5. Well, 360 divided by 5 is 72. So this, wow, that was working really good. So 72 is our count by. So our first answer is 72, and you'll put a comma between your answers when you're typing it into MyMathLab. I don't think you'll have to type in the degree symbol or anything though. So 72 is the first. Yeah, it just has, I was looking in MyMathLab and it just has the degree symbol there for you. So you'll just type in the number 72. Okay, so that was our first answer, and we're just going to keep counting by 72. So we will add 72, which is 144, would be our next answer with the comma, and then we'll just keep that process going. We're just going to keep counting out by 72. So we get 216 as our next answer. And we're looking for 4 answers here, so we have one more. And that last answer is 288. So this is our answer for MyMathLab. And again, if you want to do a quick check, you can add one more time and you should get back to 360. So that's just a way of like checking to make sure you did it right. Okay, so the last thing in this lesson is about tilings or tessellations. A tiling is an arrangement of polygons that interlock perfectly without overlapping. Some tilings use irregular polygons. Some use regular polygons. If they have a pattern that is repeating throughout the tiling, they're called periodic. There are some tilings that are aperiodic. The ones that you see on the screen are all periodic in some way. So the types of questions that MyMathLab are going to ask you about tilings are, it's just going to have you show a tiling or choose multiple choice a tiling from a triangle. So I'm just going to show you a couple tilings and then we're done. So if you have a shape like a quadrilateral and you want to tile it, what you would do is follow along the diagonals and repeat the shape. So quadrilateral has two diagonals, one in this direction and one in this direction, and you would just repeat the shape along the diagonals, and then you would see that diagonal repetition happening over and over again. So to kind of see that happening live, I have a trapezoid. So if I follow along the diagonals, I can create a tiling. And just keep following along the diagonals. Those newly placed also have diagonals, so you could, follow along those diagonals as well. And just keep repeating it until you have a tiling. Now, all of the shapes that I'm placing are the same. They're not rotated, they're not reflected, though they're symmetric. But in theory, it's creating these other white shapes that are actually the same but reflected. But the tiling itself is of the green shape. Whoops. Anyway, you get the idea. That's probably enough. Whoops. That's probably enough of that. For a triangle, the tiling is a little bit different. So for quadrilaterals, you follow along their diagonals. For triangles, if you want to tile them, you follow along their edges. So let me just put, so we're going to follow along these edges. So this one would go here, and then I could just repeat that. And then along the other edge as well to create the tiling. Anyway, you'll just be answering a multiple choice question about tilings, so I think you'll be able to get it just fine. Let me know what questions you have. That is it for 11B. Best of luck to you.